This video will cover batteries, including their definition, types, and specific examples of primary, secondary, and fuel cells. A battery is a storage device converting chemical energy into electrical energy. It consists of two or more electric cells connected in series, acting as a portable electrical power source. We will discuss three types: primary, secondary, and fuel/flow batteries. Primary cells undergo an irreversible chemical reaction, meaning they cannot be recharged and are used as a DC power source. Examples include dry cells and lithium cells. Requirements for primary cells include convenience, low discharge cost, and desirable standby power. The dry cell, or Leclanche cell, is made up of a zinc container anode and a graphite rod cathode, separated by a thick paste electrolyte. This diagram illustrates the structure of the Leclanche or dry cell, showing the positive and negative terminals, protective casing, electrolyte paste, and the internal components like the carbon rod and manganese dioxide mixture. The zinc manganese dioxide cell, or dry cell, has an EMF of 1.5 volts. The reactions involve oxidation at the anode and reduction at the cathode. The resulting ions combine to form a complex salt, diamine dichlorozinc, which is critical for preventing gas liberation. Advantages of these cells include a voltage range of 1.25 volts to 1.50 volts, low cost, and common use in torches, radios, and pacemakers. However, a major disadvantage is their short life due to the acidic electrolyte corroding the container, even when not in use. Lithium cells are primary cells, where lithium acts as the anode due to its lightweight, high oxidation potential, and good conductivity. They use non-aqueous solvents as electrolytes due to lithium's reactivity in aqueous solutions. Lithium cells are categorized into those with solid and liquid cathodes. The lithium cells with solid cathode, like the lithium manganese dioxide cell, use a solid electrolyte and are typically 3 volts. The reactions in a lithium cell with a solid cathode involve lithium oxidation at the anode and manganese dioxide reduction at the cathode. The net reaction is the formation of lithium manganese dioxide. Coin-type cells are used in watches and calculators, while cylindrical cells are used in cameras. Lithium cells with liquid cathodes, such as the lithium sulfur dioxide cell, utilize co-solvents. Another example is the lithium thionyl chloride cell. These cells are used for military, space applications, and in medicinal devices like neurostimulators. Secondary cells or accumulator batteries are rechargeable and can be reused repeatedly. Examples include lead-acid, nickel-cadmium, and lithium-ion batteries. They are widely used in cars, power stations, and emergency lights. They act as galvanic cells when discharging and electrolytic cells when charging. Improved performance requires small separation between electrodes, high current discharge at low temperatures, and minimal voltage variation during discharge. A high energy efficiency is required, calculated as the energy released on discharge multiplied by 100 and divided by the energy required for charge. Secondary cells should also be reliable, shock tolerant, and have a good cycle life. The lead-acid battery, commonly used in automobiles, consists of cells connected in series, each providing 2V. It uses a lead anode, a lead oxide cathode, and sulfuric acid as the electrolyte. This image illustrates the construction of a lead storage battery, showing the arrangement of positive and negative plates, the separator, and the electrolyte connections. To maximize current output, cells are connected in parallel. During discharge, the battery produces current, and reactions occur at the anode and cathode. Sulfuric acid is consumed, and when its density drops below 1.20 grams per cc, the battery requires recharging. Recharging reverses the discharge reactions. During the charging process, lead is deposited at the cathode, and lead dioxide is formed at the anode, regenerating sulfuric acid. Lead-acid batteries are advantageous due to their rechargeability, portability, and low cost, used in various sectors like railways and automobiles. However, they are fragile, and concentrated sulfuric acid is dangerous. The nickel-cadmium or NiCad cell is another rechargeable secondary cell, using cadmium as the anode and nickel dioxide as the cathode, with potassium hydroxide as the electrolyte. The reactions in the NiCad cell involve oxidation of cadmium at the anode to cadmium hydroxide. At the cathode, nickel oxyhydroxide is reduced. The overall reaction shows the reversible nature of this secondary cell. Nickel-cadmium cells are useful due to their small size and high charge/discharge capacity. They have low internal resistance, a wide temperature range, and produce about 1.4 volts. They are used in electronic devices, medical instrumentation, emergency lighting, and toys. A fuel cell is an electrochemical cell that converts the chemical energy of a readily available fuel oxidant system into electrical energy. Its basic principle is similar to an electrochemical cell, but the fuel and oxidant are continuously supplied externally to the electrodes. The output is oxidation products plus electricity. Examples include the hydrogen-oxygen and propane-oxygen fuel cells. The hydrogen-oxygen fuel cell is highly successful. It uses two porous electrodes of graphite impregnated with a catalyst and a potassium hydroxide solution as the electrolyte. Hydrogen and oxygen gases are bubbled through the anode and cathode compartments. The net reaction is the combination of hydrogen and oxygen to produce water, with an E cell of 1.23 volts. A series of these cells forms a fuel cell battery, producing electricity with byproducts like heat, carbon dioxide, and water, which minimize environmental pollution. Fuel cells are used as auxiliary energy sources in space vehicles and submarines. The water produced is a valuable source of fresh water for astronauts. Fuel cells are preferred in spacecraft due to their lightness. Advantages of fuel cells include high efficiency, reaching nearly 70%, which is better than gasoline or diesel engines. Their efficiency is independent of the power plant size, and maintenance cost is low. They are highly efficient in driving vehicles, requiring less energy consumption. Disadvantages include high initial cost, unknown accurate lifespan, and challenges with durability in storing large amounts of hydrogen. General applications of cells and batteries include emergency power from lithium cells and water-activated batteries. Standby power often uses lead-acid batteries. Medical implants require long life, low self-discharge, high reliability cells like lithium primary, button, and special cells. Cordless equipment uses NiCad and lithium-ion batteries. Finally, button and coin cells, zinc air, and silver oxide cells are used in hearing aids, watches, calculators, and other small electronics. Next, we will review the distinctions between primary, secondary, and fuel cells. We will conclude this video with a set of review questions and multiple choice questions on the material covered. Here are some multiple choice questions to test your understanding of the different types of cells and their properties. Additional multiple choice questions are provided. The answers to all multiple choice questions are provided at the end of the slide. Thank you for watching this video. The following reference books are recommended for further reading on engineering chemistry.